Welcome, everybody. Um, we are very excited to be doing this today. We have spent years and years working on ERPLAB Studio, and we think it's going to really make your lives a lot better. We've used it for analyzing a lot of our own data, and it just really makes life easier. Okay, so let's just jump in. Um, a few pieces of background information. So I will make a PDF of the slides for today available on the erpinfo.org website within 48 hours, probably sooner. We are making a recording of this. David, if you could double check to make sure it's recording, that would be good. There will be a link to the recording on erpinfo.org within 48 hours. So if you have questions, you should use the Zoom Q&A tool to ask those questions. We have 3 of the people from my lab here to answer questions. And if there's a question that I need to answer, if one of you could text me, then I will see that text and know that I need to address the question in real time, or at least that's the theory. Okay, so what are we going to do today? So we're going to first start talking about why we created ERPLAB Studio. What problem does it solve? What's its mission? Then we'll talk about some of the key features. And then I'm going to demonstrate the use of it, a set of basic processing steps for a simple experiment. So I'll describe the example experiment that we'll be going through, and then we'll apply those basic processing steps to the data from 6 subjects from that experiment. And then, if there's time, I'm going to demonstrate how artifact correction with ICA works. That's a little more involved, so I've put that off for the end. So if you don't see it during our initial basic processing steps, don't worry, we will get to it if there's time. And also at that point, I'll talk about interpolating bad channels. And I'll talk about it at that point because it's a little tricky to figure out how to combine the interpolation with the artifact correction. And then there will be time for any final questions that you have. Okay. So first, though, I want to run a little poll here and get some information about your background and experience. So go ahead and answer the poll questions. And there are several different options. You can answer more than one of them. Okay, we're getting numbers in. It looks like we have a very broad range of experience. We've got 17% of people have never used EEGLab, 23% have used it a lot, everybody else in the middle. 15% have never used the original version of ERPLAB, and 18% have used it a lot. So a lot of different people with different experience. I'm going to assume that you already know the basics of how to do ERP analyses. I can't teach you all of that and how ERPLAB Studio works at the same time. But hopefully I'll be able to cover everything that you need, whether you are an absolute beginner with EEGLab and ERPLAB, or whether you are an expert. Okay. So why did we create ERPLAB Studio? A lot of it is just that I found our existing ERPLAB, what we now call ERPLAB Classic, the plugin version that plugs into EEGLab, to be really kind of annoying sometimes. So one thing that I found annoying is I would have to like click a menu and then click a submenu and then click a submenu inside of that. And if I wanted to try something multiple times, I had to re-click the same steps over and over and over again just to do the same thing, like trying different filter parameters or different artifact rejection parameters. It was just really a lot of pointing and clicking. Another problem is that we would get requests for support asking for features that were there, but hidden away somewhere in these hierarchical menus. And it was just really hard for beginners to see. Oh, you're not seeing the screen. Man, I am not. There we go. Okay, so we've got all of these menus and submenus. It can be difficult to find what you want, and it was really hard for beginners to learn how to use it. So we train a lot of undergrads in our lab, and this is just, it was not very a good learning environment. Okay, another problem, and this was somewhat annoying to me, but I had a conversation with a guy named Michael Pitts at Reed College who said he didn't use ERPLAB with his undergrads, and the number one reason was it was hard to get a sort of topographic layout of the waveforms. You'd have it in whatever order they were recorded, and that was just not convenient. And I know that I spent a lot of time like, I need to find the CZ electrode. Where is it here? So that was an issue. Um, and then there's another issue, which is that everybody, but especially beginners, should, when you're processing data, you should always process it visually the first time, and you should look at the result of each processing step. This avoids so many problems by doing this. And then once you've processed it once visually, then you can run a script and make sure you get the same thing, because scripts don't make mistakes. Well, at least they don't make idiosyncratic mistakes the way that a human will. So it's a really good idea to do it visually and then do it with a script, make sure you get the same thing. But man, this is such a hassle with the current version of EEGLab and ERPLAB Classic, because you have to keep plotting and you have to go click on a place to get the plotting window, then adjust the plot the way you want to see it. And it was really not automatic and a pain. And then when I wrote this book on applied ERP data analysis, which has many, 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 many different exercises going through real data, I just found writing these really convoluted descriptions of what to do. It just seemed unnecessarily complicated. And then when I looked at commercial EEG ERP analysis packages, like they were just so much more visually appealing and easier to use. So we developed ERPLAB Studio. Okay, and remember, you can ask questions at any point in the Q&A tool, and David, Guanghui, and Kurt will answer them. Okay, so ERPLAB Studio is a standalone MATLAB program. So the original version of ERPLAB, ERPLAB Classic, is a plugin that runs inside of the EEGLab graphical user interface. We abandoned that for ERPLAB Studio. It's its own program, but it calls the EEGLab and ERPLAB code. You have to have MATLAB, you have to have a MATLAB license, and it has to include the signal processing toolbox, so you have to make sure you have that, which you can get from the MathWorks, just like you get MATLAB. So you have to have that to run ERPLAB. But we will eventually provide a binary version that doesn't require MATLAB. If your needs are simple, you'll just be able to run it absolutely for free, no MATLAB license, nothing like that. So maybe in a year or two, we will have that. And as you can see, you see the data and you have a set of panels down the side that allow you to do all the various processing operations. And where do you get it? Well, it's automatically included when you download ERPLAB Classic. So if you go to GitHub to download ERPLAB, or if you do it through the EEGLab GUI, either way, you'll end up with all the code that you need to run it. Now we're going to continue to support ERPLAB Classic so that you can continue to use that if you find it convenient sometimes to operate from within the EEGLab GUI. You'll be able to go back and forth between them. So basically, ERPLAB Studio is just a new user interface for the same underlying routines that we've always used. So it's EEGLab and ERPLAB, it's just a different user interface. And we have these panels along the side, and you can see that the panels are the things that you'd expect to see for things like filtering, assigning events to bins, changing the sampling rate, the epoch length, doing channel operations for things like re-referencing. And then we have all of the EEGLab ICA tools as well. And it also includes a history function. So the bottommost panel is the history, and that will show you the MATLAB equivalents, the script equivalents of everything you do in ERPLAB Studio. So if you haven't done any scripting before, EEGLab, and we just totally stole this from EEGLab. This is a brilliant feature of EEGLab, that everything you do in the graphical user interface is equivalent to a MATLAB command, and so it saves a history of the MATLAB commands. So if you want to create a script, all you have to do is do everything once in the GUI, look at the history, and that's the set of commands that go into your script. So it's a very nice, easy on-ramp to scripting. And even if you know scripting well, it's still helpful to make sure you're getting all the parameters right. So very useful feature. Okay, so in ERPLAB Studio, you always see the currently selected EEG set. That's what we now call EEG Lab calls a data set or an ERP set. So you always see the current one, and when you do an operation like filtering, you'll just automatically see the result of that operation. So here's what it looked like before you click go on the filtering. Here's what it looks like afterwards. So you get this immediate feedback. And the plotting is actually pretty quick. I think it's probably faster than what you get in EEGLab. We've spent a lot of time optimizing it to make it go quickly. If you've done ICA, you can actually see the IC activations in the same window as the EEG channel data, lined up perfectly. This makes it so much easier to figure out that, oh, this independent component number 2 is the same thing as my blinks, which are happening at the same time. Now we have separate tabs along the top for EEG data and ERP data. So you'll begin by importing your data from whatever hardware system you have, or loading existing EEG lab files. You'll do a bunch of EEG lab processing. You'll create average ERPs. And once you create average ERPs, you're taken to the ERP tab. And then you have a bunch of different processing operations for the ERPs. ERPLAB has all the same importing features as EEGLab has. So we've just used the EEGLab code for this. So you'll have access, I think, to everything that you had in the regular version of EEGLab. We are in the process of adding a third tab for ERP decoding. So about a year ago, we released a bunch of decoding tools for ERPLAB, so you can actually decode what face somebody is looking at or what they're holding in working memory from ERP data. And we're going to add a tab for that in ERPLAB Studio. So coming soon. In the longer term, we're planning to add a tab for single trial EEG measurement and analysis. This is becoming very, very important in some research areas to be able to measure things on single trials and do linear mixed effects statistical modeling. So we're working on that. That's probably going to take a couple of years before that's ready. Okay, the top panel in the EEG tab is the EEG sets panel. And that's just what we call data sets to distinguish EEG data from ERP data. So we call it EEG sets. And you load a set of EEG data, and each data set can either be continuous EEG or epoch EEG. And because different panels work with different, some work with only continuous, some work with only epoch, some work with both, you have to only be looking at one type or another at any given time. So you can see here that we've selected continuous EEG, so it has grayed out these two EEG sets, which have epoch EEG. But you can have them all loaded at the same time. It's just only some are active at a given time. Some functions operate with both epoch or continuous, like filtering. Others operate only with one type. So the artifact detection routines that we've used for years and years and years require epoch EEG data. And then along the side, you'll see that some panels are grayed out if they don't operate on the current type. So if a panel is grayed out, that just means that it won't work with the type of data that you currently have selected. So average ERPs are stored in ERP sets. So you go to the ERP tab, there's an ERP sets panel at the top. You select one or more of those ERP sets for processing. And then in the ERP sets or the ERP tab, it's very easy to specify a custom channel layout so you can have that topographic setup here where we've got our frontal pole, our midline, frontal, central, parietal, etc., our left hemisphere, right hemisphere. So it's very easy to do this. And then if you want to make publication quality plots, we have an advanced waveform viewer that again allows you to do this sort of topographic layout, but gives you much finer control so that you can make publication quality plots. And then in our measurement tool for measuring amplitudes and latencies from ERPs, we have an improved preview tool that really makes it easy to make sure that you're measuring what you think you're measuring. Okay, here's a really useful new feature. You can process multiple EEG sets or ERP sets in one step. No more activating one, doing filtering, activating the next one, doing filtering, activating the next one, doing filtering. You can just select a bunch of them at one time, filter them all together, do measurement for them all together. Whatever you want to do, you can do it for multiple ones all at the same time, with a few exceptions. Some of the EEGLab routines don't make it possible to do that. So there are a few where you can't do that, but most of the things can operate on multiple EEG sets or ERP sets in one step. That alone is worth the price of admission. So this is an example here where if I've selected multiple Epoch EEG sets and done artifact detection, I can just do it for them all at one time. And it's only going to show one at a time, but I can step through the different ones that are selected with these buttons up here. And here you can see that the ones marked in yellow have been marked for rejection. And the particular channel that led to it being marked is shown in boldface with a little square at the beginning of the waveform. By the way, we put a little blank period between the epochs so that it's easier to tell where one epoch ends and the next one begins. That was always a minor annoyance in EEGLab. Okay, so we've included in ERPLAB Studio the most common EEGLab functions and almost everything that ERPLAB can do. Including the importing of raw data and running ICA, because I know that's important to many, many, many people. So we have almost all of the ERPLAB stuff, most of the EEGLab stuff. And if there's something that's not in there, you can just run the original EEGLab. Now, you can't, so you can just run them both. And they share the same file formats and variable names. So it's very easy to do something in the original EEGLab, save the files, then open those files in ERPLAB Studio. Process them some more, save the files, open them in EEGLab. However, you can't have the EEGLab graphical user interface running at the same time as ERPLAB Studio in the same instance of MATLAB because they use the same variable names and they're not communicating with each other. So you're going to have trouble if you try to run them simultaneously. In fact, ERPLAB Studio, if it sees that EEGLab's GUI is running, it will kill EEGLab's GUI. But there's a trick for this that seems to work very well. So if you have multiple versions of MATLAB, so like on my computer, I have MATLAB 2023B, that's what I'm going to be using today, and I still have the previous version I was using, 2021B. You can run both of those versions of MATLAB at the same time, have EEGLab running in one, ERPLAB Studio running in the other. Seems to work fine. There might be a problem with that eventually, but it seems to work fine. So that makes it relatively easy to go back and forth between EEGLab's graphical user interface and ERPLAB Studio. Okay, so let's go through some basic processing steps. So first, let me just briefly describe what the typical steps are in a very simple analysis pathway. So typically you'll import the EEG file from whatever format your system creates. You'll add an event list structure. That's just an extra version of the event codes that makes it easier to do things that we require you to use in ERPLAB. So EEGLab has its list of events called eeg.event, And we make a parallel version that has additional information and is much easier to modify, see, etc. So then you'll do your typical pre-processing steps, filtering, re-referencing, interpolation, whatever you need to do. You'll perform ICA-based artifact correction somewhere in this stream of events. The order in which you do it depends on your goals, your data, etc. And then you'll start doing some ERPLAB specific stuff. And in particular, you'll assign each event code to a bin. So a bin is something like the targets, the standards, the rare, the frequent, whatever your categories of stimuli are that you're going to average together to make your average ERPs. So one bin will end up being the average ERPs from one condition. So we have a very powerful, not super intuitive, I have to say, but very powerful tool for this called Bin Lister that allows you to sort of abstractly describe what goes into your bins, like I need any instance of event codes 11, 21, or 31 that are preceded by event code 202 and followed between 200 and 1,000 milliseconds later by event code 254. So you can do something complex like that or something simple, and it will, for each event code, figure out which bin or bins it should be assigned to. Then you'll convert the continuous EEG to discrete epochs, like from 200 milliseconds before stimulus onset to 800 milliseconds afterward, or whatever you need for your experiment. And then you'll do artifact detection. That is, you'll use a set of algorithms, or you can do this by hand, and mark epochs that have artifacts in them. We don't delete them at this point. We're just marking which ones have artifacts. And then you'll do the averaging process. And when you're averaging, you will ordinarily have the averaging routine exclude any epochs that were marked as having artifacts. So this creates an ERP set, and it will open up the ERP tab. And then you'll do your ERP processing. And there are many processes you might do, including like combining bins or channels, like making difference waves, making clusters of electrodes, whatever you need to do with your ERPs, plotting the waveforms, plotting scalp maps, and measuring amplitudes and latencies. And when you measure your amplitudes and latencies, you'll export the values to a text file. Eventually, will allow you to export to an Excel file. And then you just import those data into your favorite statistics package and do the statistics there. So ERPLAB does not include any statistical analyses. This was a design decision we made a long time ago. And the reason is basically that there are too many possibilities for statistical analysis. And if we made a couple available to you, then people would use them even when they weren't appropriate. You see this sort of thing all the time. People will do what's easy instead of what's right. I don't want to be responsible for people using the wrong statistical techniques. So you're on your own for statistics, but we allow you to export the data in a format. We have a couple of different export formats for the amplitudes and latencies that are convenient for different kinds of statistical packages. Okay, so those are the steps, and we're going to demonstrate them today with a particular experiment. This is the N400 paradigm from the ERP core. So the ERP core is a set of 6 common experimental paradigms where we have created optimized versions of them. Each paradigm takes only about 10 minutes to run. We have data from 40 neurotypical college students, so you can see what typical data should look like. And we have all of the analysis scripts in EEGLab and ERPLAB, so you can see how we analyze our data. So I encourage you to look this up and use it. It's got all kinds of uses. People have published papers using our data. The more, the merrier. Okay, so I want to go through what the paradigm is like so that the analyses make sense. So this is a very typical primed target paradigm. So in each trial, you get a prime word and a target word, and the task is to press one of 2 buttons to indicate whether the target word was related or unrelated to the target or to the prime word for that trial. And then you get a new prime and a new target. So you press a button for each target to indicate whether it was related or unrelated to the preceding prime. And you just have many, many of those pairs over a period of about 10 minutes or so. And if you average the ERPs to the targets, separating them into those that were related to the prime word or unrelated to the prime word, you get very typical N400 results. So here's the ERP at the CPZ electrode site for the related, and you get, sort of broad sustained positivity. And for the unrelated, you get an N400 that's added on to that and drives it in a more negative going direction. And you can isolate the N400 by making an unrelated minus related difference wave, and that gives you totally prototypical N400 component. So we're gonna go from the data. The data have already been imported. I don't want to demonstrate that. They've been imported into EEGLab, saved in EEGLab's file format. Then I'm going to take you through all the steps that it takes to process the EEG data and get to the point where you can plot these difference waves, measure the amplitudes, save them to a file for statistical analysis. Okay, but in order to do this, we need to understand the event code structure for this experiment. So we had two different lists of words. This was used for counterbalancing purposes. And we have prime words and we have target words. So there's an event code for each word, the prime and the target. The event code indicates whether the word is a prime or a target, indicates whether it was related or unrelated to either the following word for the prime or the previous word for the target, which word list it came from. Okay, so like event code 121 is a prime from a prime word that's unrelated to the following target that came from list 1. And we have 30 occurrences of each of these different event codes. We also have event codes for the responses. So we have an event code of 201 when a correct response occurs, and an event code of 202 when an incorrect response occurs. The number of those is around 30, around 30 times 4, but it depends because subjects make errors. So it's not exactly 120 for each of them. Okay, to download the data, you could download the data from the ERP core, but for this example, we're doing just a subset of the data. We've got 6 subjects, and they've been pre-processed a little bit already to make this easier. By the way, the analyses that I'm going to go through are sort of a simplified version of what you can find in the ERPLAB Studio tutorial on the ERPLAB website on GitHub. Okay, so you can download the data, and the data are stored on box.com. I wouldn't recommend doing this now, but if you want to run through this yourself, you click on this link. It'll take you to a place where you can download the data. It'll look like this. You click on the little button here, and it will download the files. You'll want to name them Studio Tutorial files. If you are in a country where you're not allowed access to box.com, like China, you can get it from the Baidu Cloud Storage platform. Here's the password right there. Okay, so you'll download the data, and then you'll go through a set of processing steps. So as I just said, this is going to be a simplified version of what's in the ERPLAB Studio tutorial. And I'm going to do a couple of things a little differently just for simplicity's sake. So here's the link to the tutorial, and you can go there and run through all of this yourself after we're done today. To launch ERPLAB Studio, once you have it all installed and you've got your path right, you simply type eStudio. And it's a complicated piece of software with hundreds of thousands of lines of code. So it takes 20 seconds or so to launch on my computer. And it gives you some feedback along the way about the different components that it's getting launched. So it takes some time. It is what it is. So it's first launching the tools for the EEG tab. Now it's launching the tools for the ERP tab. Once they're all ready, the graphical user interface will appear. Okay, so that took 30 seconds to launch. So here we have our graphical user interface. And there's an EEG panel. There's an ERP panel over here. So I clicked on the ERP panel. They both have a way of loading data at the top. And let's see. So So the first thing that I would ordinarily need to do is set the current folder to be where the data are. And in MATLAB, you can set the current folder. It's shown up here, and you can set it from there. Or you can just set it with the current folder button in the EEG sets or ERP sets menu. And so you would navigate to the folder that has the data. I'm already there, and you click open. And the current folder is going to be the first place that MATLAB looks for files. And if you save a file without specifying a path, it's going to save it in that folder. So we have a folder here that actually, well, you'll see in a second. So I'm clicking load because I want to load the data. And so here's the contents of that folder. So it just has a bunch of data files. And I'm going to load the EEG set from subject 6 in the N400 experiment. So I just click that. You can click multiple ones all at the same time if you want to. So you don't have to do them one at a time. You can click many at the same time. Ones that are not the right file format are grayed out. So a .erp file is an ERP set. I'm trying to load an EEG set, so it grays out the ERP set. So I click OK, and it takes a moment to load it, but it's reasonably quick. And as soon as you load it, you see the data. With the original version of EEGLab, every time I would load a file, I would then have to click a bunch of things to view it and make sure I was looking at the right thing. You don't have to do that, just automatically appears. You can turn off the automatic plotting here. So automatic plotting is on. If I click that, it will turn it to off. So if you're on a really slow computer and the constant replotting of stuff is slowing you down, you could turn it off, but ordinarily it's on. Okay, so here we have our EEG. And so there's an EEG sets panel. You can select which channels to show, whatever you want to do, and click apply. And now it's just showing those channels. Or we can go back and click all to show all of the channels. Down here, we have some plot settings. One of them is the time range to plot. That's 5 seconds. So we're looking at 5 seconds of data here. Then we can scroll by clicking the plus X button. So that's plus 5 seconds, another plus 5 seconds. Or you can skim ahead by more by 5 times X, so 25 seconds at a time. You can see there are lots of blinks here. In these experiments, in the ERP core experiments, we didn't tell subjects anything. We didn't tell them not to blink. So there are lots of blinks. So this is great for using ICA to get rid of blinks. But if you're not using ICA to get rid of blinks, you're going to throw out a lot of trials because of blinks. So it's easy to do that. You can do, here's something I really recommend doing. Set the time range to some huge number like 600 seconds. And then you can plot the whole session. It's going to take I have to click apply. It's going to take a second. And now you can see the whole session. Okay, lots of weird stuff going on here. By the way, these are the event codes. So you've got lots and lots of event codes. And then there's a gap because there was a break. We had like a 15-second break after the first set of event codes. And then we had another block of trials and then a break. So that's what we're looking at there. If you want to, you can turn off showing the event codes or turn it back on and go back to a 5-second plot window. And now we're back to normal again. Okay. Now let me show you what the end result is going to look like for this subject by loading an ERP set. So I've already made the ERP set for this subject. So I went to the EEG tab, I clicked load, and I told it to load the ERP set for subject 6. And now we have the ERPs for all of the different channels in the order they are on the cap. So that's not very useful, but it's very easy to say, I want to just show channels PZ, CPZ, and CZ. Click apply. And now we have just those 3 channels. It's also easy enough to plot scalp maps. So we're going to do the scalp map of the mean amplitude between 300 and 500 milliseconds And we'll just do the bins 3 and 4 are the unrelated or related and unrelated targets. So you tell it which bins you want to plot, which time range you want to plot. And there are a lot of other options to get fancy if you want, but I don't want to get fancy here. So here it has the scout maps. This is the target word that's related to the previous prime. So you're mostly seeing P3 here. Here's the unrelated one. So you're seeing a mixture of N400 and P3. So easy enough to save those plots. And then you go to the file menu and you can save this as any number of different formats. My favorite one is scalable vector graphics. Very good format. Okay, so that's how you make a scout map. Okay, so this is what we want to get to. We want to get to the ability to do that. But we're starting with our EEG. So we're going to go through all of the basic pre-processing steps so you can see how to do it. Okay, so let's go back to, no. So I've already shown you that there are these, actually, let's look at it again. I'm going to go back to a ridiculously long time range. I click apply, and it changes it to 397 milliseconds because that's the maximum time in this plot. And so we have all these slow drifts, okay? If you're not doing high pass filtering, you have slow drifts in your data. And I encourage you to look at your data at like 5 minutes at a time. You'll realize stuff is going on that you did not realize if you're looking at just a few seconds at a time. Okay, so let's go back to our 5 seconds. Okay, so now we're going to demonstrate filtering. So we go down here and we open our filtering panel. And this is a simplified version of the very complicated filtering tool that we have in ERPLAB Classic. If you want the full thing, you can click on this advanced button and then you'll get all kinds of options. And they're very useful. It shows you the impulse response function, all kinds of stuff. But usually you don't want to do that. So we're going to just be simple here. So we're going to do a filter from 0.1 hertz to 30 hertz. So high pass cutoff at 0.1, low pass at 30, and a roll off of 12 decibels per octave. I strongly recommend a roll off of 12 decibels per octave unless you really know what you're doing and understand how convolutions work and why you get time domain distortion when you have steep roll-offs. Okay, and then there's this remove DC offset, which just leave it on if it's on. Our recommended value there is almost always the right thing. So you set those values, and you click run. And then here it's showing us the name of the new EEG set that it's going to create. So an idea that we inherited from EEGLab is that most processing operations create a new data structure, a new EEG set, which you can save to a file or not. You don't have to save it as a file and clutter up your disk, but you're going to end up with your original data, your data that have been filtered, the data that have been filtered plus something else, and you end up with all of those there, which makes it really easy to say, oh, I want to step back 3 steps and do those previous steps over again. So the name of our original EEG set was 6_N400, and it's recommending a name of 6_N400_filt for the new EEG set. Now you can just edit this to be whatever you want, or you can change the suffix here. So I could change it to something like filt 0.1 to 30 and add the suffix to the EEG name, and it does that. So you can name it anything you want, but I recommend using our suggested names sort of as your default and then changing them to other things when you need to. Having defaults really makes it easy to know what you've done and look back at your previous data and know what it means. Okay, so we just click OK, and it's filtering and it's done. Okay, so if we now go back up to the EEG sets menu, we see our original EEG set, 6_N400, and our filtered one. And so you can go back and forth between them. So it's just made a new copy of the data, filter that new copy. So we have our original data, our filtered data. Easy, easy, easy. So the next step is we're going to add this event list to our data. So we already have event codes in there, but the event list is this sort of more convenient way of storing the event codes that allows you to, for example, export them as a text file, modify them, and then re-import them in case you need to add new event codes, change something, etc. I have a colleague just yesterday who was using this because she was analyzing the data from an experiment using auditorily presented words, and the event codes gave the sort of nominal onset time of the different words. But spoken words, some words take longer to start than others. So there were variable delays from word to word. So she was adjusting each event code to match the actual time of onset. And then she could just import that back in and it will change the event codes. So this is a very convenient feature. Okay, so we go to the event list panel. We click create to create the event list, and it's going to create it from the existing event codes. And usually this is very simple. You just want to accept the defaults usually. So it's going to do a little funny thing with what are called boundary codes. This is like if you have multiple blocks and you stop recording between them, you'll have a boundary between them. So we have to convert that into a special code of -99. And then if you're using a Brain Products data acquisition system like the ActiveChamp system, you need this button clicked so that it will convert the text-based event codes to numeric event codes. Okay, and then you click Create, and it creates or it asks you what you want the new event code to be called, or the new EEG set to be called, and it's going to append EList for event list onto the name. So I just click OK. And now that becomes the active EEG set. Okay, so now if we go to the event list panel, we can click View and view our event list. ERPs are event-related potentials. The word event is in the name. So the events are super important. So we make it much, much easier to see your event information than what's possible in EEGLab. So when you click on View, you see some sort of header information at the top, like the name of the set and the sampling rate. And then here are the different events. So the item number, just 1 through however many events you have. The bin epoch is not used yet. It'll be used later. Here's the event code. It can also have a text label. Here's the onset time of the event code in seconds. Here's the difference in event code time between the current event code and the previous one in milliseconds. The file format allows for a duration. We don't use it, but it could be there. Then there are some flags. And then there's an enable bit that allows you to turn event codes on or off if you want to. And then eventually we're going to put bins into each one of these. We'll assign different event codes to different bins. Okay, so we've created an event list from our data that we have. Okay, so now we're going to demonstrate assigning event codes to bins. So we have our different event code structure, like we know what each event code means, and we want to turn this kind of list into these 4 bins. So we're going to have primes that are followed by a related target, primes that are followed by an unrelated target. Those two, the ERPs for those two should be identical plus or minus noise, because unless our subjects have ESP, they don't know whether the next target is going to be related or unrelated, but it's kind of nice to have that just in case. The main analysis, though, will look at the targets. So these are the target words that were either preceded by a related prime or preceded by an unrelated prime. And in both cases, we're going to require that they're followed by a correct response. And the way that we do this is we create an abstract description of each one of these bins in terms of the event codes. So you'll create this file. It's a text file called a bin descriptor file. And it's not super complicated, but also not super user-friendly. We are going to replace this eventually. And this just says, okay, you have a list of event codes within the curly brackets. The dot before it means that the event codes following the dot are the time locking event, time 0. So this is just the event codes for prime words that are related to a subsequent target. These are prime words related to a subsequent unrelated target. Target words that are related to the previous prime are 211 and 212. 201 is the event code for a correct response. So this is saying we're going to time lock to instances of 211 or 212 that are followed 200 to 1500 milliseconds later by event code 201. So that's how we say that it's related to a previous prime, because that's what the event codes indicate, and followed by a correct response. If you didn't follow that, don't worry about it. You can read our documentation. We have extensive documentation about how this works. Okay, so let me show you how this works in practice. So we have our tool here for assigning events to bins with bin lister. We're going to find our bin descriptor file. So that's the file that I was just showing you that has the text that describes how to convert event codes into bins. So that's what's in this file. So we tell it that file, and then we just say run. And there are a bunch of other options that you can get with the advanced, but you're unlikely to use them. So we put them in this advanced button. Okay, so now it gives us the name, the suggested name for the new EEG set that it's going to create. You could call this anything you want. You could edit it here. You could edit the suffix, do whatever you want, but I'm just going to keep the default. If you wanted to save this to disk as well, you'd say save EEG sets to disk. We recommend using a file name that's the same as the EEG name. You don't have to, but it gets confusing if you don't. So we recommend doing that. Okay. I'm not going to actually save this. Okay, so it runs bin lister, and now it has created it. And you'll notice that now we have this table here that says for bin 1, here's the description of it, we have 60 occurrences. So we have 60 prime words followed by a related target, 60 prime words followed by an unrelated target. There were 30 for each word list, but we're collapsing across the word lists here. And then we've got target words that were related, target words that were unrelated, and that's less than 60 because people made some incorrect responses or late responses. Okay. The next step is going to be artifact detection. Sorry, the next step is going to be epoching. So we're going to convert the continuous EEG into epoch EEG with extract bin-based epochs. So you tell it the time period. So this says we want to go from 200 milliseconds before stimulus onset to 800 milliseconds after stimulus onset. We're going to do baseline correction using the pre-stimulus interval. You could use the whole interval, the post-stimulus interval, none, or specify whatever interval you want. Then you click apply. And it's going to recommend adding BE for bin epoch to the end of the EEG set name. We click OK. And now we have very different looking data because it's epoch data, right? So now epoch is selected up here, and all of the continuous EEG sets are grayed out. I could go back to the continuous EEG by clicking that, or back to the epoch by clicking epoch. Okay, and again, you could scroll through here. And now in the plot settings, what we have here is the number of epochs. So I could say, I want to look at just one epoch at a time. And now you have a sort of stretched out version of one epoch. But 5 is usually a pretty good number to look at. Okay, so we're looking at all of our epochs. The event code at time 0 is now replaced with the bin number along with the event code. So this means this event code is for something that's going to go into bin 4, but the original event code was 221. And so that's the stimulus. And and there's a response after it. So this is a target word. So here's the event code for the response. Here's the prime word, no response, because subjects only make responses to the prime words. Okay, now we're ready to do artifact detection. So we go to our artifact detection panel, and I'm going to use there are many different algorithms that you could use for detecting artifacts. So you can just do a simple voltage threshold. Like if the voltage gets greater than plus 100 or less than minus 100 microvolts, we're going to mark that for rejection. That's occasionally useful, but for detecting blinks, there are much better algorithms. So the step-like artifacts is really the best. So I tell it I want to use that algorithm, and I'm going to do it just from the vertical EOG channel. So I clicked browse to browse through my channels. Text is kind of small. I hope you can see that. So that's vertical EOG. I click OK, or I could have just typed the number in there if I happen to know it. And that's this vertical EOG channel down here. And we've already converted that to be a bipolar recording. So it's under minus over. By the way, if you have your artifacts down at the bottom, you can see they're being cut off. So there's a trick for that. So I can say that I want a bigger buffer at the top and bottom of the window. So right now it's 100%. I'm going to set it to 300%. Click apply. And now it has more buffer there so you can see more of the waveform. So that's just a handy trick so that you can actually see whatever is in the top and bottom channels and it won't get cut off. Okay, so back to artifact detection. So we're going to look for step-like artifacts in channel 30. We're going to look at it in the entire time epoch. Now you'll see here the epoch goes from minus 200 to 795, not 800. That's just sort of rounding. We have a sampling rate here of 200 hertz. There's a sample every 5 milliseconds, and so it stopped at 795. Okay, so we're going to specify the threshold. How big does the voltage have to be in order to be considered an artifact? I'm going to make the threshold 50, and I'm going to leave those other things set the way they are. I click run, and it asks me for the name of the new EEG set that it's going to create. Puts AR for artifact rejection on the end. I say OK. And now it shows me a table. Before it shows me the EEG data with the artifact detection, it shows me a table of how many trials were included versus rejected. And you really want to look at that before you look at the data, because if you're seeing that 98% of your trials were rejected, you know you've done something wrong. Or if only 2% were rejected, you've probably done something wrong unless you've already done something like ICA to get rid of the artifacts. So here it's showing you the total percentage of trials that were rejected, so almost 40% of trials, because these subjects weren't told to suppress blinking. So this is totally expected. And you can see it here broken down by each of the bins. Okay, so we say close, and now it's going to show us our new data. And now it has, let's see, we'll go back to the beginning. So now any epochs that had artifacts are marked. So you can see that it's shaded in yellow, and you can see that the vertical EOG channel 30 is in boldface with a little square here. So it's showing you that that's the channel that caused this epoch to be rejected or marked for rejection. And you can just scroll through and you can see, hey, it's done a pretty good job. Okay, now if you don't like the job it's done, you can manually change things. Or if you're dealing with very small data sets and you just only want to use manual artifact detection, you can do that. So you click on manual detection and you say view and mark. And now it pops up a new window in a second here. Spread that out. And now I can just click on that and it unmarks it. And I can click on that one and it marks it. So you can just go through and change whatever you want to change. Oh, sorry, clicking the wrong button. There we go. Change whatever you want to change. And then you click the mark button to actually mark them. And then it will create a new one called manual mark at the end. I'm going to click OK. And now if we go up here, we see that one. Now I just did random stuff there, so I don't like that one. So I can just click clear to get rid of that EEG set. And now it's gone. So you can do a lot of basic steps here. You can make copies, you can rename, you can do all kinds of things. You can append multiple EEG sets together. So if you've got like 5 different files per subject, you can merge them all together. You can append them all together just by selecting them here and clicking append, and that will create a new one that merges them all together. Okay, so we now have our artifacts marked, so it's time to finally create an average ERP. So we go down here to compute average ERPs, and you'll see that only works on Epic EEG. And the default is we're going to exclude any epochs that were marked during artifact detection. Highly recommended. You could ignore the artifact detections if you wanted to. And there are actually times where like you just want to do the ones that are marked, but ordinarily we'll exclude the ones that are marked for artifact detection. We, a few years ago, developed an ERP data quantification method called the standardized measurement error. That's on by default. So when you compute your average ERPs, you'll get data quality information. So ordinarily just leave that to the default parameters. You can customize it if you know what you're doing, but just leave it on default for most people. Click run. Again, it gives us a window for naming it, but now we're creating an ERP set. And I don't want that. I just want to call this 6_N400 because this is the initial ERP for this subject. So I'm going to call it that. And ordinarily, when you make the ERP, you're going to want to save it to the disk. So if you leave MATLAB and come back later, you still have access to it. And again, you typically use the ERP name as the file name. But I'm not going to do that now. I already have a copy of this saved on my disk. Okay, I say OK, and it runs. And it gives me this table of information here so you can see what happened. And again, it tells you how many total trials there were in each bin. This is very important. You should know how many trials there should be, and you should check to make sure that you're getting the right number. Because if you're not, for example, imagine you're only getting 3 or 4 trials per bin here, that means something probably went wrong in an earlier stage. So always good to check that. It also gives you a quick summary of data quality. So we have this measure called the standardized measurement error, or SME, and we have a couple of different versions of it. The one that we can calculate at this point is called the analytic SME, or ASME, and it gives you here what that value is, what the median value was, the minimum and the maximum for all of your channels and all of your bins that you just created. And the median is not usually exactly 1.0. That just is some random thing that happened here. And these numbers probably don't make any sense to you right now. But once you've done this for a while and you get used to what's normal, you're going to notice, oh, this value is 35. Usually I'm seeing values of about, 3 to 4 or 5. Something's going wrong here. So this is just a quick and dirty way of seeing, is there something wrong with your data in terms of the data quality? Okay, then you can export this information into a text file or an Excel file so that you can, if you want to like do a summary in your results section of how many trials were included versus excluded, you can just save that information, put it into Excel, and calculate that and report it in your paper. Okay, we can close that. And because we've now created an ERP, it has taken us to the ERP tab. So we were in the EEG tab before. Now we're in the ERP tab, and here's the ERP set we just created. Now I had already loaded an ERP set with the same name. That's why that's in there twice. So I'm going to get rid of the one that I had loaded before. I'll just select it and click clear. Okay, so this is the one that I just created. It remembered what channels I had set from before, so it's just showing those channels. And here we see the different bins that are available. So we have our 4 bins. So if we look at our prime words, so these are prime words that were related or unrelated to the following target. That's not of much interest here. So let's look at the target words that were related or unrelated to the preceding prime. So we can see that the unrelated is more negative than the related in the N400 time window. And that's our basic N400 effect. You can also click all to see all of the channels. And there are a variety of different plot settings that you can do if you want to change the time range or the vertical scaling, or if you want to plot it in a different layout, like a topographically oriented layout. Okay, so let's do that. But what I'm going to do first is, and this is a thing you're going to want to do from time to time, I'm going to reset all of my settings. So I've probably changed things away from their defaults. And so if something looks weird, it might be because I changed some setting before. So if you click this reset button down here, you'll get this little GUI that allows you to restore the default parameters for the ERP panels, for the EEG panels. You can also clear the EEG sets and ERP sets if you want. But I'm just going to restore the panels. Actually, I'm going to restore them for both the EEG and ERP panels. Okay, so now it has restored everything. Let's go back to just plotting the targets. Okay, so better ways to organize our data. So if you have sort of standard 1020 system channel labels, you can click this button, Simple 1020 System Order, and then it will do it in a semi-rational order. So any channels that don't have 1020 labels are going to come first. And then it does it, takes the most anterior electrodes and goes left to right. So that's FP1 and FP2. Then it goes back to the next set, goes left to right, F7, F3, FC, F4, F8. Then it goes to the next one back, which is the frontocentral, C3, FC3, FC, FC4. So that's a somewhat more rational order than what we had before. So that's a useful thing sometimes. But what's really useful is to click the Custom button. And this allows you to create a simple spreadsheet that specifies where each channel should go. And it takes a few minutes to do that the first time, but then you can just use it over and over again for every subject, every experiment. So I'm not going to show you the process of creating it. I'm just going to import one that I've already created. And I can show you what that looks like, I think. Not so easily. So it's just a simple spreadsheet with grid, it's a grid of locations because that's what a spreadsheet is. And it's just the names of each electrode where you want them to go. Okay, so I selected that. I click Apply. With all the plotting stuff, you have to click Apply for it to work. And now we have this very simple layout where we have the midline, left hemisphere, right hemisphere going from front to back. And I just stuck the vertical EOG and horizontal EOG electrodes up there. Okay, so now we have the data plotted in a nice, simple, easy to find layout. Let's see. Another thing that I wanted to show you is this ERP and bin information panel. So in the original version of ERPLAB and EEGLab, it takes some poking around to find the information you want. We've tried to make everything easily available in these panels. So here's the name of the ERP. Here's the file name that it was saved at. Sampling rate, epoch, goes from -200 to 795. Number of channels, number of bins, and then here are the different bins, the number of trials per bin, the original number of trials, the number of accepted, number of rejected. And then I can click this bin info table button and see a more detailed table like you saw after we finished averaging that has the summary of the data quality. And again, you can export this if you want. Okay, so that's easily available for you. Okay, so the next thing I'm going to do is show you how to make difference waves. But I'm also going to show you how to operate on multiple different ERP sets at the same time. So I'm going to clear the one that I just created, and I'm going to load the one so I've already created previously these 6 averaged ERPs. So I'm just command clicking them to select multiple ones as you would do ordinarily. And I've loaded all 6 of them. And now ordinarily just the last one is selected, but I'm going to shift click to select all of them. Now you can see which one it's actually plotting up here. So it's only plotting one of them, but I could click here, this next button, to plot the next one. So now it's plotting the second one, and it's showing you here that it's that one. Okay, so I'll go back to the first one, and now I'm going to make a difference wave, a unrelated minus related difference wave. So I'm going to do that with something called bin operations. So in bin operations, you type in simple mathematical formulas that tell it what to do. So I'm typing in bin 5 equals bin 4 minus bin 3, and the label is going to be unrelated minus related. So this is how you make a difference wave. I just say, okay, I'm creating a new bin 5, and it's equal to the bin 4 minus bin 3. And I'm telling it I want to modify the existing ERP set. You can also do this in a way that it creates a new ERP set, which is useful under many conditions. Okay, now I've got all 6 of these selected, so when I say run, it's going to run it on all 6 of them. Okay, so it's running them, and it's done. And I can tell that it's done because now we have a bin 5, which is unrelated minus related. And you can see it's plotted in there, but I'm going to show just the related targets, the unrelated targets, and the difference wave. Okay, so we have related, unrelated, and difference wave. So very easy to create a difference wave, but also you know exactly what you're doing because you're saying it's bin 4 minus bin 3. And you can do all kinds of different equations here. Many, many, many different kinds of equations, whatever your heart desires. Okay, so now we have the data. You can see there's a lot of high frequency noise. So the next thing we're going to do is we're going to apply a low pass filter. So these data have been high pass filtered in the EEG, but I didn't apply a low pass filter to the EEG when I made these averages. So I'm going to go to the filtering panel, and I'm going to filter it at, let's see, what am I supposed to do? 20 hertz. I'm going to filter at 20 hertz, no high pass filter. You do not ordinarily apply high pass filters to average ERPs. So low pass filter at 20 hertz, and I click run. Okay, so now it's creating a new ERP set for each one of those 6 ERP sets because I had all 6 selected here, so it's going to filter all 6 of them. And you can see that it's adding the underscore filt to all of the new ERP names. And now you can see why it's nice to be able to have something here. So I can just say, I want to change that to filt 20, and it changes it in all of them. And if I wanted to save them to disk, I could just click that and it will save all 6 of them to disk. But I'm not going to do that. So I click OK. It's filtering them and it's done. And now you can see we've got the filtered version here. And we have all 6 of the filtered ones selected here. So now I can do some other operation on all 6 of them. Now it's only showing the first one here, and we can go through and scroll through and show the other ones as well, but I'm not going to demonstrate that here. So now you can see the high frequency noise is gone. We still have a lot of probably unaveraged out alpha in this subject, but hey, single subject data. Okay, now I'm going to demonstrate something called channel operations. So in bin operations, you're recombining the different bins, and you do it the same way for every channel. In channel operations, you create new channels by recombining the existing channels, and you do the same thing for each bin. Okay, so let's go to channel operations. And what I'm going to do here is I'm going to create a cluster channel. This is going to be a new channel that's the average of the CZ, CPZ, and PZ electrode sites. So these three electrode sites here. And that's the sort of thing that you might want to do prior to measuring the amplitude. So instead of measuring it separately at all three sites, you might want to create a cluster. This is very useful when you have high electrode densities. You get better measurements from clusters. You don't have as many p-values. A lot of reasons to do that. So we're going to create an equation here. And I'm just copying and pasting it to make it faster, but ordinarily you would type it in. And you can have multiple equations here. So, so if we go back to our bin and channel selection, you can see that we've got 30 channels. And so I want to create a new channel 31. And the new channel 31 is equal to channel 21 plus 14 plus 13 divided by 3, because those are the channels that we want. So here's 14, 13, 21. So CZ, PZ, and CPZ. So the sum of those divided by 3 is the average of those 3. And then I'm going to label it the centroparietal cluster. And I still have the filtered ERP set selected. So when I run this, and again, I'm modifying the existing ERP sets. So when I run this, it's just modifying these ones. So it's not creating new ones. But we can see down here that now we have this channel 31, this centroparietal cluster. Now it's not plotting it here because I don't have it listed in this channel layout. So I'm just going to go back to my plot settings. And instead of custom, I'm going to go to default. And I'm going to tell it that I want to plot the original 3 that I made the cluster of, plus the cluster, except I did that wrong. Click apply. Okay, so here's our PZ, our CPZ, our CZ, and this new channel is just the average of those 3 sites. Okay, so that's how you can recombine your channels. And I'll show you at a later point how you can also use the channel operations, which can apply to either EEG sets or ERP sets. You can use it for re-referencing your data. So we'll show you that a little later. And you can do that on either averaged ERPs or continuous EEG. Okay. So the next thing I'm going to show you how to do is how to make a grand average. So we're going to go down here to average across ERP sets. So ordinarily, averaging across ERP sets is used to make a grand average, but there are other uses for it as well. So imagine you have separate ERPs, you ran each subject in 2 sessions, you have separate ERP sets for each session. You could combine the ERP sets together using this function. One thing that we're doing here when we're making our grand average ERP is we're going to compute the point-by-point standard error of the mean. Actually, let me just show you that for the single subject data. Okay, so here's a single subject data. And when you average the data, you can create the standard error of the mean at each point in time. And then you can plot that. Now, when I made the unrelated minus related difference wave, I don't know what the standard error of that is, so there is no standard error there. Also, if we look at the filtered data, it doesn't know what the standard error at each time point is for the filtered data. So if you filter before averaging, then you can get the standard error at each time point for the average ERP. But if you filter after averaging, how would it know what the standard error is? Okay, so let's go back to our 6 filtered ERP sets. And we are going to compute the point-by-point standard error of the mean. And here it's the standard error of the mean across subjects. And we click run, and it's going to suggest a name of grand. So I'm just going to leave it as that. So it's computing a grand average of those 6 subjects. And now you can see I have a new ERP set called grand. And a grand average is just an ERP set like any other ERP set. There's nothing different about the structure. You can do all the same things to a grand average that you can to any other average. And now I'm going to turn showing the standard error back on. And now you can see the standard error of the mean. And now we have it for the difference wave as well, because now this is the standard error of the mean across subjects, not the standard error of the mean across trials. Okay, so that's making a grand average. So in an experiment, you pre-process your EEG, you do artifact detection, maybe artifact correction, you epoch your data, you make average ERPs, you plot the average ERPs, you do some additional processing like making difference waves, you make a grand average across subjects, you visualize it, showing the standard error. And by the way, I saw a question came up, I will answer it for everybody. You can easily export this by going down here to plotting options and saying save figure as, and that will save that figure in whatever format you want. Again, I like SVG. I think it's a great format, but you can do PDF or various bitmap formats. Or you can go here to the advanced waveform viewer, and that is much better if you're trying to make publication quality figures. It gives you much more precise control over what the plot looks like. And then you can export that if you would like. Okay, so we've made our grand average. We've done everything. We're ready to do our statistical analysis. So we want to measure the, in this case, the mean amplitude between 300 and 500 milliseconds to get our N400s. So I've selected the filtered ERP sets from each subject, and I go down here to the measurement tool, and you can measure different things. You can measure mean amplitude, positive peaks, negative peaks, amplitudes and latencies, fractional area latency, rectified area, lots of different things you can measure. We're going to say we're going to measure it from ERP sets 1, 2, 3, 4, 5, and 6. No, I don't want to do that. I want the filtered ones. So let me, instead of that, I will browse. So I want those. So 7 through 12. 7:12 is MATLAB's way of saying we want everything, all the integers between 7 and 12. I'm just going to want to do this from the target words that are related versus unrelated to the preceding prime, so bins 3 or 4. For channels, let's see, I'm going to do, for this example, I will do PZ, CPZ, and CZ. Ordinarily I would just do it from the cluster, but I want to show you what it looks like with multiple channels. The time window that I want to measure, so conventional window for N400 would be 300 to 500 milliseconds. Give it the name of a file like N400 mean amplitude. And if you click options here, you can specify the path for it. If you don't specify the path, it will just go in the current folder. And there are a couple of different file formats depending on what you want to do. So there are a variety of options there. And so now we're ready. But before you click Save My Measures, I recommend previewing because this is an easy way to realize, oh, I've put in the wrong measurement parameters. So then you get this preview window. And I'm going to say, well, I want to show all of my channels. So we've got each of the 3 channels there. And I want to overlay all 6 of the different ERP sets. So now we can easily see, okay, that looks reasonable. And this is bin 3. And here we have a table of the actual measures, right? Just so you can kind of see what's going on. If you wanted to save this as a plot, you could click this Create Static Exportable Plot, and then it would allow you to save it to your disk. And so this is bin 3, and I could say, okay, now show me bin 4. Or I could overlay all of the bins and channels at the same time, but that's a little much. So go back here. And so here are the 6 subjects at PZ, at CZ, or CPZ, at CZ, and these are the related targets and the unrelated targets. So looks good. Everything looks fine. So I click Close. And now I click Save Measures. And now it has created a file in that folder called N400 mean amplitude. So now I'm going to reveal what's been going on behind me in the MATLAB window. So if things, like every time something is running, all kinds of information gets plotted here. And if things aren't working right, take a look at this command window, and you might find some warning messages or be able to figure out why things aren't working right. So very useful thing to look at if things aren't working well. Also, it's giving you here the MATLAB command that's equivalent to the last step. So this would be the actual command for a script that you would type to do the measurement. You can also see all the files in the current folder here, including the one that I just created. I can double click on that, and here are my measurements. And this is in a tab delimited format. Be very easy to import that into Excel or into whatever statistical package you use. Okay, so we have gotten to the point of creating all of our measurements for our statistical analysis. Now what I want to do is show you re-referencing. So first I want to tell you a little bit about it, but only a little bit, because otherwise this would take hours. So if you want to understand the underlying logic of this, you can see Chapter 5 in an Introduction to the Event-Related Potential Techniques, 2nd edition, available on Amazon.com. So brief little bit of logic. In most cases, the EEG from all sites are initially recorded relative either to ground or to the same reference electrode. And so imagine that we call that reference electrode R, or if you're using a biosemi system, this is going to be like recorded relative to CMS. You can think of the FZ channel as being the difference between the voltage at the FZ electrode and the voltage at the reference electrode. The voltage at CZ is the difference between CZ and the reference. So if I wanted to re-reference to CZ, if I wanted to make CZ the reference, well, that's FZ minus CZ. That's what I want to get. I want the voltage at the CZ electrode minus the voltage at, the voltage at the FZ electrode minus the voltage at the CZ electrode. Well, it turns out that I can just take this original FZ minus reference and minus CZ minus reference. And if you do that, well, we have minus R minus minus R. The R's drop out, and that just gives us FZ minus CZ. So to create the data reference to CZ, I just subtract the CZ channel from every other channel. And we do this using channel operations, where we can create simple equations. So for example, CZ is channel 21, So I'm going to create a new channel 1 that's the old channel 1, which was FP1, minus the old channel 21, which is CZ. So this is the original FP1 to the reference minus CZ to the reference. If I do that difference between them, that gives me FP1 reference to CZ. Okay, and so I need an equation like this for every single channel. That's 30 equations. That's a lot of channels. So you could type all of those equations in, but we have something called the reference assistant that makes that easier and less error prone. So I'm going to show you that in a second. And it can be done on EEG or ERPs, and usually you'll do it on your EEG, but I'm going to demonstrate it using the ERPs because I have that grand average all loaded up and it'll just be simpler that way. Okay, so let me go to the grand average. Oops. Select the grand average. And I'm going to go back to just showing CPZ, PZ, and CZ. Actually, no, I'm not going to do that. I'm going to say, I'll leave it at all. But I'm going to go back to my custom layout. Okay, here's the grand average with the custom layout. And I'm going to re-reference everything to the CZ electrode site. This is not something you would ordinarily do. Usually you do something like re-reference to the mastoids or to the average of all sites, but it's just simpler to demonstrate this with CZ. Okay, so going to go back to channel operations. I'm going to clear the equations that I had before, and I'm going to click on Reference Assistant. I'm going to tell it that I want to use channel 21 as the reference. And you can read the documentation for that. But I'm going to exclude channels 28 and 29. Those are my horizontal and vertical EOG channels. They were already bipolar channels. I don't want to re-reference those. So I want to re-reference everything to channel 21. And you could do something more complicated like the average of two channels if you want to do the average of your references. And I click OK. And now it gives me all of these equations. New channel 1 equals channel 1 minus channel 21, label FP1. New channel 2 equals channel 2, etc. Now here I'm creating a new ERP set from the old one. So I have a new channel 1 equals the old channel 1 minus channel 21. And I do that for all these channels. And I told it not to do channels 29 and 30. So I thought I did. I must have made a mistake. Let me try that again. Reference Assistant, channel 21. And I also realized I still have that cluster channel. So I'm going to tell it not to do 29, 28, 29. Sorry, I did the wrong channels. 29, 30, and 31. There we go. That's what I did wrong. Okay, so now you'll see it's subtracting channel 1 from every channel, but it's not doing it from these 3 channels. Okay, now I click Run, and it's suggesting a name of grand_chop for channel operations. But I'm going to call this re-ref. Okay, so now it has re-referenced everything to CZ. And somehow the labels got messed up here. Anyway, I'm going to try re-importing that, see if that fixes it. Well, something got messed up. But in any case, this is supposed to be the CZ channel. CZ minus CZ is 0, so we've lost that. And we've changed a bunch of the different channels. Okay, let's see. What else do I want to show you? So there's also a way to do this where you're re-referencing to the average of all sites. Very easy to do. Running low on time, so I'm not going to show that to you. So the next thing I'm going to do is I'm going to show you how to do ICA-based artifact correction. So I'm going to clear my existing EEG sets. And I'm going to load an EEG set from a different experiment. This is now going to be from a mismatch negativity or MMN experiment. And I've chosen this just because it's a simpler case. So here we have the data from this experiment. I'm going to show you the entire recording. So again, lots of event codes, so that makes it hard to see what's going on. So here are our data. So obviously we need to filter out the low frequencies before we do anything else. So I'm going to go to filtering, and I'm going to tell it to filter from 0.1 to 30. Okay, now we have our filter data, looks much better. Now there are a couple of weird things in the data, some like points where the subject did something weird and created a large artifact. So we can easily see that here, or we can go back to 5 seconds. And you can see all this junk at the beginning because this is before the trial block has started. I want to show the event codes again. Okay, but once we start getting the stimuli coming, the subject calms down and the EEG is calmer. Okay, so let me say just a couple of words about artifact correction. So the way that ICA works is it uses the pattern of covariation across data, across time points, to come up with the time course and scalp distribution of a set of independent components, or ICs. So to remove an artifact, what we do is, well, we can decompose the data into the components. Hopefully there will be one or two that are clearly artifact components, and we just reconstruct the data, leaving out the artifact components. Now, this only is valid if the artifact has a consistent scalp distribution for the recording session. So blinks, very consistent scalp distribution. EKG, very consistent scalp distribution. Muscle noise, like movement artifacts, not consistent. So it doesn't work with things like that. So ICA is a statistical technique. It doesn't know about electricity or electrodes or voltages or anything. It just knows that it has a bunch of samples from different variables. That's all it knows. And it has an algorithm that learns how to unmix. And so we think of the EEG as at any given electrode site as the mixture of many different sources. Well, it learns an unmixing matrix that turns the scalp voltages into time courses of underlying independent components. And so you have, for each component, you have the time course of that component, like the amplitude over time, and you have the scalp topography of that component. Now, ICA starts with random weights. So if you repeat the process multiple times, each time it will be slightly different. That's okay. So what it does is it finds the set of independent components that are maximally independent and can also fit your data. So it doesn't know anything about voltages, dipoles, branes, anything. It's just finding components that are independent of each other. So here's a figure from a very early study from Scott McCaig's lab. So here's one epoch of EEG. And so, can see a blink here, you can see muscle noise there, and the blink spreads to multiple electrode sites. Once you apply ICA to the entire data set, we can say, okay, well, here's the time course of these 22 components. One thing that you'll get is the number of components will be equal to the number of channels. So we have 22 independent components. We have a time course for each of them. And you can see components 1 and 2 both look like they're doing the blink thing, whereas component 13 looks like it's doing the left hemisphere muscle noise, and component 15 is doing the right hemisphere muscle noise. So to create the corrected EEG, you just recombine all of the independent components, leaving out the artifacts, and then you get the corrected EEG. So that's the basic idea. Okay. And I wish I had time to tell you more, but we are running low on time. So to actually do this, so I'm going to show you a simple version of this. This is the way we were doing it up until about 3 or 4 years ago. There's a way to make this work a lot better, but this is going to be simpler. So the first thing I'm going to do here is I'm going to make bipolar vertical EOG channels. So the data here, what we have are the vertical EOG is just the voltage at this lower electrode relative to the reference, and we have left and right horizontal. So I'm going to make bipolar channels here. So I'm going to so this data set has 32 or 31 channels. So I'm going to create a new channel 32. That's channel 31 minus channel 15. That's the under the eye minus the FP2, I think, above the eye. So that's going to give us our vertical horizontal EOG. And then I'm going to do the horizontal EOG. It's just channel 30 minus channel 29. And I click run. And it has done it. So if I look down here, now I have a VEOG bipolar channel and an HEOG bipolar, and you can see them down here. And if I scroll through the data, you can see that we have the blink in the VEOG bipolar, as well as in all the other channels where blinks normally appear. Okay, so we have got our continuous EEG. It's got blinks in it. So there are some weird periods of sort of crap in here. Ordinarily, I would delete those periods before running the EEG. Just delete them completely from the EEG. But I don't have time to show that to you now. So a very simple thing that we will do here to run ICA is we go to the EEGLab ICA panel and we say decompose data. That's the process of running the ICA algorithm in order to extract the components. And we're going to leave out the bipolar EOG channels because that will allow us to actually, by excluding those and not correcting for them, we'll be able to see, oh, here's where the blinks were in the bipolar, and that will allow us to see that they've been corrected. Okay, so ICA takes a while to run. So it's running here. You can stop it if you want to, but it's going to run for a minute or so. So I'm just going to let it run. And while it's running, I'm going to explain a little bit about how I would really do this, the professional way to do this. So ICA gives you as many components as you have channels. And it's really not enough components. No matter how many channels you have, there are more underlying sources of brain activity than you have channels. There are millions of sources of underlying activity because each neuron really is an independent, is a source of activity. So you don't have enough channels. And what that means is that ICA is going to end up taking multiple true components and merging them together into a single independent component. And we don't want that to happen. And if you've got a lot of junk in your data, low frequency drifts, periods where the subjects are yawning, you'll end up wasting ICs on that junk. So the way that we really do this is we have our EEG and we make a copy of it that's super heavily filtered, and we deleted all the junk out of it and stuff like that. And we get our ICA components from that cleaned up data set. Still has the blinks in it, but it doesn't have all the other junk in it. Then we transfer the ICA components back to the original data set and then remove the blinks from that new data set. Okay, it's finished running. So we're going to call it add ICA onto the end of the name. And now we look up here and we have our data set that has the independent components added to it. So now what we can do is we can tell it to display those independent components. So we've got the channel data and the independent components. We tell it to display both. So here are our channels up here, and here are our independent components down here. So if we scroll ahead, you can see, okay, here's a blink. Here's our vertical EOG, and you see it in all these different channels. And we can see that independent component 8 has the same time course as our blinks. And actually, we're going to make this a little easier to see. I'm going to just plot the top 10 independent components. Okay, so you can see independent component 8 has the same time course as the blinks. Whenever there's a blink, you have this component. So that's the component we want to get rid of. So we want to reconstruct the data from all of the components except independent component number 8. And the way we do that is with actually, let's also look at the scalp topography of the components. So if you do this inspect and label ICs, you'll be able to see the scalp map of every component. And you can see component 8 up here has the kind of scalp map you'd expect for an eye blink. It should be right up here. Okay, and you can also do other things here. You can label which ones are artifacts and stuff like that. It's in the documentation. I'm not going to explain that now. Now, while this is showing, you can't do anything else in ERPLAB, and that's what this window up here says. So once we're done with this, we can click close, click OK, and now we're back able to do what we want to do. So now we're going to remove that independent component. So we say remove ICs. So we say we want to remove independent component number 8. We click OK. Here's the name of it. And now we didn't apply ICA to our bipolar channels, so you can still see the blinks in this bipolar channel here. So you know that that's where the subject blinked. They're blinking here. But now all of the blink activity is gone from all of the other channels. So we have eliminated the blink activity, or I should really say dramatically reduced the blink activity in the data. Okay, now to really do this, you'll want to use this cleaned up data set, as I mentioned before. So I strongly recommend that you go to the Applied ERP Data Analysis book, read Chapter 9, which is going to explain the right way to do this. And I can tell you that since we've been doing it this better way, we've had much better results. And in a study where we have 300 subjects measured from 5 different sites, and they are a control group and people with schizophrenia, bipolar disorder, major depressive disorder. And we have like 8 data sets from each of 300 subjects. And, you know, it's noisy data. It's patient data collected at multiple different sites. When ICA was done without this optimized version, about 20% of the subjects couldn't be kept. Using the cleaned up version, like 99% of them could be kept. So you definitely want to do this. It definitely works much better. Okay. That is the end of the demonstration. So I only have a couple of minutes for questions, but if there are any remaining questions, feel free to ask them. Looks like, oh, here we go. Using ERPs, ICA to isolate real ERPs. Scott McCaig, who was the person who first started using ICA with EEG data, would say, oh, totally, you should do that. I do not do that. ICA makes assumptions that are known to be false. If you use ICA to try to get real components, it's guaranteed not to work perfectly. How imperfectly it works is hard to say. So I definitely do not recommend using ICA for anything other than artifact correction. Works great for correcting blanks, reasonably well for correcting eye movements, great for EKG. Only use it for rejecting like known artifacts. If it's something you don't know what it is, like just do artifact rejection for weird occasional things. ASR before ICA, that can be very valuable. Okay, so in my new book, Applied ERP Data Analysis, hi Heather, we suggest don't re-reference to the average of the left and right mastoids until after ICA. The reason is, so it is possible to do, but you are more likely to accidentally do something wrong if you've done something other than referencing to a single site. To avoid making errors, strongly recommend that you reference all electrodes to a single electrode prior to ICA, and then re-reference after the ICA. There are other ways that can work, but you're just more likely to make mistakes. Okay, when should you interpolate electrodes? You should go to my new book, Applied ERP Data Analysis. There is an appendix at the end on the order of operations, and it will explain the order in which to do it. It's a little bit tricky, but I don't have time to go through it now. PCA for isolating time windows. PCA, I'm not a fan of using PCA with ERP data because it does not even come close to match. The assumptions of PCA don't come close to matching the assumptions of, or the truth about EEG. There are exceptions to that. So spatiotemporal PCA can be useful in some conditions, but generic PCA I haven't found to be very useful. Okay. So if you've got movement artifacts, ICA is not usually good for those because ICA absolutely requires that the scalp distribution is always the same, and movement artifacts tend to vary from one movement to another. So you just need to use artifact detection and rejection for movement artifacts. Okay, so EEGLab has this IC label routine built into it that can automatically try to figure out what your different ICs are, which artifacts they are. We have found, and other experts I've talked to have reported the same thing, that it only kind of works, and that if you're really using it, if you really want to get things done properly, you have to go and check it and adjust things. So, so you can use it, but I would not recommend just believing it. You might need to adjust it. It is, however, very useful if you are first learning how to do ICA and you have no idea what you're doing. You can use its suggestions to help guide you. A better thing is to have an expert in your lab or a neighboring lab show you how to do it. But if you don't have that, the IC label routine can be very useful as a learning tool. Okay, so I don't recommend using PCA to account for interpolated electrodes before ICA, simply because it's complicated and you're likely to make mistakes. So in the appendix of the new book, just follow the order of operations it describes there, and then you won't have any problems. Works like a charm. Okay, I have to run now, but thank you all for coming. I hope you use it, share it with other people. Make sure to cite our original ERPLAB paper in any publications you have so that we can keep our grant money coming in so that we can keep creating new products. Okay, thank you all very much. And hopefully I will run into you at one conference or another.